Okay, in this video I'm going to continue on my tutorial series on thermodynamics and statistical mechanics. This is tutorial number 10 and this is part of the subsection on Einstein Solids. So this is the third tutorial on Einstein Solids, and in this tutorial we're going to discuss what the meaning of heat is. So we're going to actually see where heat comes from. The previous video to this is Einstein Solid number 2, where we discussed, and I suppose we didn't really prove it because we've proven it already, but we discussed the multiplicity of an Einstein solid. So let's do some very quick revision. What is an Einstein solid? An Einstein solid is where we imagine that the solid, the energy stored in the solid is being stored by some linear harmonic oscillators, and that each atom is a linear harmonic oscillator, and it's quantized, of course, and that it vibrates at different frequencies and as a result has different quantized energy levels. And what we did then was we tried to work out the number of microstates and the number of macrostates which an Einstein solid would have. And we found really that because we require all the energy to go into one of the macrostates, we found that the multiplicity of a macrostate was equal to 1. In other words, there was only one way to have, say, a certain amount of energy in a certain particular macrostate, and that was that. But then when we delve down into the microstates, corresponding to each of the macrostates, we had a formula which looked like the following. Q was the number of units of energy, N was the number of oscillators, minus 1 factorial divided by Q factorial and N minus 1 factorial. And this is for one particular microstate. The microstates for one macrostate. And in order to get all of the microstates, we had to sum over all the macrostates. And the reason we didn't use multiplying over all the macrostates is because all these states are dependent on each other and they are not independent like they would have been, for example, when I discussed the quantum statistics. So I think that's pretty much where we are. Now that's a bit of revision. If you want, you can accept that and look at this tutorial as just this tutorial on heat. So what we're going to do is now we're going to discuss two Einstein solids, we'll say A and B, and they're weakly interacting. So basically they interact just enough so that energy can go from B to A or A to B, whichever way, but it can go one way or the other. And what we'd like to see is if you bring these two solids together with, say, energy level of UA, total energy here, and U sub B here, what will the equilibrium energy be? And what are the number of microstates, or the multiplicities corresponding with the different possible macrostates of this particular combined system? So that's what we want to do, and by looking at that we'll see what heat really is. So remember now, heat by definition is energy energy in transit. So it shouldn't surprise you that we're talking about a movement of energy from a hot body to a cold body. Okay, so how do we start? Well, the way we start is as follows. We set up a problem. So I'm going to set up that U sub A is the energy in Einstein solid A. But you need to remember that the quantized energy values are h nu, and we have Q values of energy. So the total energy is h nu times Q sub A, and the total energy in Einstein solid B is equal to h nu times Q sub B. Now we could analyze this problem by either talking about U sub A and U sub B, or Q sub A and Q sub B, because there's only this constant h nu in the difference. So for that reason I'm going to talk about Q values rather than U values, just because it's easier. So let's think of this interacting system whereby there are 6 units total in energy. So Q total is equal to Q sub A plus Q sub B is equal to 6 units of energy. So that would mean, of course, that U sub total is equal to 6 times h nu. Next, let's say that there are the same number of oscillators in each solid. And we're going to say that there are 3 oscillators in each solid. So there are 3 atoms, we'll say. Let's say for argument's sake 3 atoms, each atom having only one oscillator. even though, to be honest, they would have more. So let's just go with that. So what we're going to do is we're going to analyze the first Einstein solid first. So if there are between Q is equal to 0 and Q is equal to 6 possible states in this particular system. So that means there are 7 possible macro states for the system. You can think of Q sub A or Q sub B, but for argument's sake I'm going to go with Q sub A. So the macro states of 1, 2, 3, 4, 5, 6 and 7 correspond to Q equals 0, 1, 2, 3, 4, 5 or 6, or of course U is equal to Q times H nu, where nu is the frequency, or Q is equal to U is equal to Q times HF, whichever one you want. So that is the energy of the system. So let's see if we can work out what the multiplicity of Einstein solid A is when it has anywhere between 0 and 6 units of energy, when it has 3 harmonic oscillators. So that's a pretty straightforward problem, because we already know what the formula for the multiplicity of a particular macro state is. So let's say this is macro state 1, where Q is equal to 0, and what we're going to have is 0 plus 3 minus 1 factorial divided by 0 factorial and 3 minus 1 factorial. And I showed in the last video why 0 factorial is equal to 1, so the multiplicity here is going to be equal to 1. So let's get the multiplicity of macro state number 2, where the energy is equal to 1 unit of energy. Actually, take that back. I'm going to go for macro state 3, because that's the one that I've done in my notes, which are beside me. So 2 units of energy, and this is macro state number 3. So that's going to be equal to 2 plus 3 minus 1 factorial divided by 2 factorial and 2 factorial, giving us a multiplicity of 6. Alright, so, and I'll just show you the answer for one more, giving it the multiplicity of Q is equal to 6, which means it's macro state number 7, S is equal to 7. We get a multiplicity of 28. Alright, so we see that the multiplicity is getting bigger and bigger, going from 0 units of energy up to 6 units of energy, with a maximum multiplicity of 28. Now of course, if solid A has those multiplicities, well, so does solid B. So we now know what the multiplicities of each of the macro states are for solid B also. Now you got to remember that if B has a certain amount of energy and it transfers to A, well then it's after affecting the amount of energy in B. So in many respects they are dependent, but we need to look about multiplying the multiplicities of A and the multiplicities of B in order to get the total multiplicity. So we need to multiply it together. Okay, and that should make sense in order to get the maximum possible multiplicity. So let's look at the following. If we have, let's say Q sub A, we have the multiplicity of A, Q sub B, the multiplicity of B, and the total multiplicity, which is the omega A, or the multiplicity of A multiplied by the multiplicity of B. So the macro states are, as we know, between 0 and 6 units of energy. And vice versa here, so this is going to be 0, 1, 2, 3, 4, 5, 6. We know that the multiplicities are as follows: that's 28, 21, 15, 10, 6, 3 and 1. And then this would be the complete opposite: 28, 21, 15, 10, 6, 3, 1. So the overall multiplicity, omega sub total, is then multiplied together. So we get 28, 63, 90, 100, and then it goes back down like this, 90, 63, 28. So looking at that should tell you something. First of all, we can see that it repeats, so it's kind of like a Gaussian function, if that makes any sense. It just, the numbers look like it would fit into some form of a Gaussian. Alright, next, which one has the maximum multiplicity? Well, the maximum multiplicity, as we can see, has a value of 100. Well, what values of energy does that correspond to? It corresponds to when there is an equal amount of energy in Einstein solid A and Einstein solid B. Alright, so there are 3 units of energy in each. So we know from the probability of something happening, so the probability of state n is equal to the multiplicity of state n divided by the multiplicity of them all. So the most probable macro state is the one with the greatest multiplicity. So clearly, this case, this macro state, where there are 3 units of energy in A and 3 units of energy in B, is the most probable. But think about it now. What's after happening here is the system is after settling into an equilibrium when there's an equal amount of energy in it. So that's kind of what happens after heat is flown. Heat flows from hot to cold and keeps flowing until everything is in equilibrium. So basically what we can say is we can return to the fundamental assumption of statistical mechanics, that over long timescales all microstates are equally likely. However, some macrostates are more probable than others. So let's go back to this probability. Actually, just very quickly to illustrate what we were saying a moment ago, if we plot Q sub A on the x-axis, Q sub B on the y-axis, what am I doing? Q sub A on the x-axis, the maximum multiplicity on the y-axis, we will get a parabola looking like this, centered at 100 and centered at 3. Okay, exactly as we saw a moment ago. Alright, so what I'm going to show you now is the probability of some of these events occurring. So this is going to be the multiplicity, the macro state. Say, let's look at just 6 of them. I don't know why I didn't look at all of them, but anyway, so we have 63 over 462, which is the total multiplicity, and we get 13%. We have 90 over 462, which works out at 19%. The 3, we have 100 over 462, giving us 21%, 19%, and 13%. And then we have another one. But the point here is we're looking at 21%. So for the most likely macro state has a probability of 21%. So that doesn't look like it's particularly more probable than the others. However, if you look at larger systems where there's more energy and more oscillators, then in actual fact this multiplicity function gets particularly sharp, and I'll discuss the sharpness of the multiplicity function at a later stage. So the whole point of this really is as follows. We had energy in either A or energy in B or both, and energy then was shared between each of the systems until the system came to its most likely macro state, in this case where both A and B had the same amount of energy. And we know this because it's the most probable macro state, as it has 100 or 21% of we'll say the total number of available states. So what we can say is as follows. Let's say, for example, Q total, so all the energy was in solid B. Then after, we'll say, a time, I don't know, let's say it doesn't matter how much time, let's say the relaxation time, it is overwhelmingly probable. It's overwhelmingly probable that Q total will be evenly spread, that Q total is evenly spread between, of course, solid A and solid B. So then if we swap this, we start with all the energy in solid A and none of the energy in solid B, After the relaxation time, it's overwhelmingly probable that Q total is evenly spread between solid A and solid B. So what we found is that heat is not a physical law, but rather a probabilistic fact. So the flow of heat stops when the system is in its most likely macro state. So therefore we can say that the heat flow stops when the system is in most likely macro state. In the most likely macro state. Okay, so that's really what we're trying to get at with this with these Einstein solids. So they were just a very simple way to look at the transfer of energy between two different solids, because their multiplicity functions are pretty straightforward, and we see as a result that heat flow stops when the system is in its most likely macro state. So that's all I've got to say about that. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you also have a bit of time, you might also click on an ad. Thank you.